Welcome to The Explainer. Today we're digging in, literally, to the hidden science that keeps our entire world standing, soil mechanics. This is the engineering that makes sure the ground under our skyscrapers, our dams, and our bridges doesn't just give way.
You know, we walk on it, we build on it, we trust it to be solid. But here's the thing, sometimes it's not. The one question every geotechnical engineer has to answer is this: what on earth makes the ground fail?
To really get to the bottom of that, we first need to appreciate how we even began to understand this, well, deceptive material. It's a pretty young science, actually, but its roots go way, way back.
This timeline really shows you that this wasn't some overnight discovery. For centuries, brilliant minds were just chipping away at the problem. You had Coulomb way back in 1776, then Darcy and Rankine in the mid-1800s. But the real game changer, the moment it all came together, was in 1925 with Karl Terzaghi. He's called the father of soil mechanics for a reason. He's the one who finally put all the pieces together and turned the study of dirt into a real, rigorous science.
So what did these pioneers figure out? Well, the very first step, the absolute cornerstone of the entire field, is to understand what soil actually is from an engineering point of view.
So here it is, the first big insight. To an engineer, soil isn't just ground. It's this jumble of mineral grains and organic stuff, but, and this is the important part, it's all about the empty space between those solid particles, because that space is filled with liquid and gas. This means soil isn't one solid thing. It's a complex, three-part system.
And these are the three ingredients. You've got the solid particles, you've got water, and you've got air. The ratio between them, well, that's the key to everything. It dictates the soil's strength, its stability, how it's going to behave when you put a giant building on top of it. It is all in the mix.
Now, to manage this mix, engineers have some very precise terms to measure those void spaces. Things like void ratio, porosity, and degree of saturation. Now, they might sound like just academic terms, but they're really vital diagnostics, because that empty space, that's where the failure often begins.
So, if the voids are the problem, the solution seems kind of obvious, right? You've got to reduce them. And engineers have two main techniques for doing that, for densifying the soil and making it stronger.
Okay, now this is a really crucial distinction. On the left, you've got compaction. Think of those giant, heavy rollers you see on a construction site. That's a fast mechanical process that literally pushes the air out of the voids. But on the right, you've got consolidation. This is the slow game. This is when the weight of a structure, over months or even years, slowly squeezes the water out. So two different techniques, tackling two different parts of that void space.
But get this, here's a fascinating little twist. Water isn't always the enemy. This quote explains it perfectly. During compaction, a certain amount of water is actually a good thing. It acts like a lubricant, helping all those solid particles slide past each other into a tighter, stronger arrangement. Too little water, and there's too much friction. Too much water, and it just gets in the way. It's a real balancing act.
But that's what happens when water just sits in the voids. What happens when it starts moving through them? Well, this is where we get into some of the most dangerous phenomena in all of soil mechanics.
Okay, think of soil particles like a pile of tiny bricks. Their own weight pushes them together, creating friction, and that friction is what holds the pile strong. Engineers call that friction effective stress. But when water starts flowing upward through the soil, a process called seepage, it creates this drag force that actually starts to lift the bricks. It pushes them apart, which reduces that friction and weakens the whole pile.
Now, if that upward flow of water gets strong enough, it can completely counteract the weight of the soil particles. And at that point, the effective stress, that friction holding everything together, it just drops all the way down to zero.
And when that friction disappears, you get what's known as a quick condition. You and I know it by a much more dramatic name, quicksand. The soil loses all its strength and literally behaves like a liquid. It just can't support any weight at all.
So how do engineers fight back against these incredible invisible forces? How do they design massive structures like dams so they're safe from these kinds of dangers?
Well, this is one of the most clever solutions out there, the filter. So imagine water seeping under a dam. It can start carrying those tiny soil particles away with it, creating a little tunnel or a pipe. And if that pipe grows, it could cause a catastrophic failure. So an engineered filter is this layer of material that's coarse enough to let the water pass through and relieve the pressure, but it's also fine enough to physically block the soil particles from getting washed away. It's so simple, but it's incredibly effective. Okay,
Let's pull all these ideas together and really look at the big picture of what we've just uncovered.
So let's just quickly recap. First, remember soil is that three-phase system: solids, water, and air. Second, its strength all depends on managing the voids between those solids. Third, engineers do this through compaction and consolidation. And finally, they always have to account for the dangerous forces of moving water. Really, geotechnical engineering is the invisible science that makes sure our visible world has a safe and secure foundation to stand on.
And that leaves us with a final thought. As we build bigger and taller, as we put more and more demands on the ground beneath us, the challenges for soil mechanics are only going to get bigger. Mastering this unseen science is more critical right now than it has ever been.